Hello, I am Eduardo from the Machine Reference Unit. For this second Cartesi Experimentation Week, I decided to not really create a dApp, but to research a solution for a problem that many asked me about before, that is, how to perform inference of a large language model inside the machine emulator. While thinking on the problem, I came up with the machine accelerated kernels idea, which is a low-level way to offload specialized computation to the host CPU. I have to say that this presentation will be very technical and I am sorry for this. First, let me explain the problem. It's a fact that large language models are too computational intensive to run inside the emulator. Past Cartesi projects try to do this, but so far they have only run in host mode, meaning would be impractical to run fraud proofs or tiny models. When we compare running a model with the emulator and natively on an Intel 14th Gen CPU, the slowdown can be up to 7,000, not only due to emulation, but also for not using all cores and instructions provided in the host CPU. And there is no magic optimization we can do inside the emulator that's able to fill that gap. To really accomplish this, we need to invent a new way to offload heavy computations outside the emulator. To overcome the present problem, these were the project goals. First, to profile and understand what on large language models are computational intensive. Secondly, research a way to offload the most computational intensive routine to the host CPU. Finally, run the inference of a Llama 2 7B quantized model in a reasonable amount of time inside the emulator. The project chose to work with llama2.c project by Andrei to perform inference, due to its simplicity to hack. What computations are heavy on large language models? If you run a profile on llama2.c, we will notice that 99% of the time is spent inside the matmul routine that only performs matrix multiplication. My hypothesis is that if we can accelerate just this routine to run on the host, we could have orders of magnitude speedups. If we inspect the matmul routine, it's simple and just 20 lines of C code. It basically performs a for loop in parallel while doing multiplication and addition of integers and floating point numbers. It also needs to access memory that we will need to share with the host. The project idea is to offload matmul computation outside the emulator. In order to do this, there are a few offload constraints to keep in mind. It must be compatible with fault proofs, it must be parallelizable on the host CPU, it must be deterministic, and finally it must share memory between the emulated machine and the host machine. After thinking about this, I came up with the following strategy. Convert matmul to a shared library on the host so the emulator can run its accelerated version. Convert matmul to a RISC-V kernel inside the machine so the computation can be reproducible during fraud proofs. Create a new RISC-V instruction that can execute matmul in a single machine cycle. And finally, patch llama2.c to use the matmul kernel to accelerate it. To convert matmul to a small RISC-V kernel, I moved its implementation to this C++ file, then modified it to be reproducible by using software floating point. When the matmul kernel is running in the host, it will run the for loop in parallel and take advantage of all CPU cores. When the matmul kernel finishes running inside the emulator, a special instruction halts its computation and switches back the context to the Linux kernel. As the matmul kernel runs in two different environments, it's needed to compile it twice and generate different files. The first generated file is the .bin freestyle RISC-V binary that really works similar to a Linux kernel, but it's a tiny kernel in just 100 bytes. The second generated file is the .eco share library, which contains the same matmul routine, but it's really an accelerated version of it that runs on the host, taking advantage of EVX instructions and all CPU cores. Both files are compiled from the same source file, but to different targets. The next step was to patch llama2.c to use it. In order to do this, mostly two changes were needed. The first change replaced the original matmul routine to execute a custom RISC-V instructions that the emulator understands as execution of the matmul kernel. These instructions will either call the matmul share library on the host or instantiate a second Cartesi machine with the matmul RISC-V kernel until it halts. The second change replaces all matrix allocation routines to use a special allocator capable of sharing gigabytes of contiguous memory with the host. The Cartesi machine emulator was also patched to be capable of running the Matmul kernel. The most notable change was the addition of an environment variable that when set the emulator uses it to execute the accelerated Matmul kernel. Otherwise, the emulator runs the RISC-V Matmul kernel, which was combined with the Linux kernel. The other parameters are details on how to run the Llama 2 model. Before trying the Llama 2 model, I made a benchmark with a smaller model. On the left side is the inference of running it with the Matmul kernel acceleration, which takes about 6 seconds to inference 100 tokens. On the right side is the inference of running it with the emulated Matmul kernel, which takes about 2 minutes. So therefore, there was a 20x speedup on inference for this smaller model, a noticeable improvement. The inference output also matched because of the deterministic Matmul function implemented. Now to reach the project final goal, I run the bigger Llama 2 7 billion model. On the left, you see it took about a minute to do inference of 100 tokens, more than 1 token per second, not bad. On the right, you see it took about 2 hours to do inference of the same 100 tokens without the Matmul acceleration. Overall, the speedup was 120x in this case, faster than the smaller model, probably because the Matmul are more computational intensive on larger models. You can check the source code for this project on this repository.